Hello friends, unit number 2, radiating element and arrays, and today's topics is finite dipole. Now in that finite dipole, the arrangement of dipole is available in the figure, and it is oriented in a z direction. Now whenever we are analyzing the radiation characteristic of the linear dipole of any length, this particular radiation will be divided in three different field regions that we already studied. Number one is the reactive near field region. Number two is the radiating near field, or it is called as the Fresnel region. And number three is the far field or the Fraunhofer region. Now in that case, to reduce the mathematical complexities, it will be assumed that the dipole has a negligible diameter, and this is a good approximation provided the diameter is considerably small than the operating wavelength. Now here, from the given figure, we need to calculate the vector potential of the particular magnetic vector potential for the particular equation. And this is the equation: Az of mu upon 4 pi integration of minus L by 2 to L by 2 I of e raised to j k capital R upon capital R d of z. Now this capital R will be written over there for the radiation purpose, because in finite dipole we already saw in a figure that the particular axis have the z of z dash cos of theta component. We get it here. So for the far region we will consider this component over there. So here the capital R is replaced by the R minus z dash cos of theta, whereas the below denominator part capital R is replaced by the small r. So this Az equation will be modified as a mu upon 4 pi integral part of minus L by 2 to L by 2 I of e raised to j k in a bracket R minus z dash cos of theta bracket complete divided by small r and d of z. After integrating this part, the sum of the components are constant, like it is not related with the z component, and that's why we are collecting this component mu e raised to j k r upon 4 pi r. This is the constant, and we are rest part integrating one over the period of minus L by 2 to the L by 2, and it is IE of e raised to plus j k z dash cos of theta d of z. Now for the far region, the same equation we are adopting one, and we are getting it the same equation over there in between the at the time of the particular analysis, and the last same equation we are getting one, and based on that, now from the figure we already know that the finite dipole antenna is subdivided into the number of infinitesimal dipoles of length del of z. As the number of subdivision is increased, each infinitesimal dipole approaches a length d of z dash. For an infinitesimal dipole of length dz dash position along the z axis at z dash, the electric and magnetic field component in the far field regions are given by this equation: d of E0 approximately equal to j eta k of IE in bracket z dash bracket complete e raised to jk into r upon 4 pi capital R sin of theta d of dz dash, whereas d of h phi approximately equal to j k IE z dash e raised to minus j k capital R upon 4 pi r sin of theta dz theta. Here we assume that the particular capital R value which is observed over there, this is approximately equal to R minus z dash cos of theta. It is for the phase term, because the little bit deviation takes place from capital R and small r which are observed in the figure, whereas capital R approximately equal to R for the amplitude term. So both the components which are radiating one, probably it might have the same amplitude but a little bit differed by the phases. So if we observe the equations over there, so d of E0 approximately equal to j eta k of I z dash e raised to minus jk in bracket r minus z dash cos of theta bracket complete upon 4 pi r sin theta d of z dash. Now if you try to separate and integrate the component over there, so E of theta is equal to, we are getting it, the blue color part is called as the element factor and the integrating part is called as a space factor. So here we are applying the pattern rule. So here the total field of antenna is equal to the product of the element and the space factor. This is referred to as a pattern multiplication for the continuously distributed sources. And here we can see the pattern multiplication rule specifically. Now we are observing the ideal current distribution. So I of E is equal to Az cap I0 sin of k L by 2 minus Z dash for the length of 0 to L by 2, whereas Az dash Az cap I0 sin of k in a bracket L by 2 plus Z dash for the length of minus L by 2 to the 0. So this is the ideal sinusoidal current will be developed across the dipole. Now if you see the E of theta, these are the complex terms we are getting one which are need to be modified properly. So we are applying the equation integral part of e raised to alpha x sin of beta x plus gamma bracket complete d of x is equal to e raised to alpha x upon alpha square plus beta square in a bracket alpha sin beta x plus gamma minus beta cos of in a bracket beta x plus gamma bracket complete, where the alpha term is the j plus or minus j k cos theta, beta term is plus or minus k, and the gamma term is k L upon 2. So this equation will be modified accordingly that. And finally we get it the equation E of theta over there, that is the after some mathematical manipulations we get it this equation. So E of theta is equal to j eta I 0 e raised to minus j k r upon 2 pi r whole bracket in that cos of k L by 2 into cos of theta minus cos of k L by 2 upon the whole term of sin of theta. So this is whichever we observe the term, this is the constant term for the given condition, and that's why it is called as the C, and the rest component is called as the field pattern. Whereas h of phi is the E theta upon the eta value. So in a similar manner we obtained the relationship between the E theta and the h phi in the far field, which is related with the h of phi approximately equal to E theta upon eta value, which is the intrinsic impedance available over there, and where C is the constant. Now here we need to observe the average power density of the particular signal. So for the dipole, the average pointing vector can be written as here W average is equal to 1 by 2 real term of in bracket E into H complex conjugate. So this is equal to the 1 by 2 real term of A theta E theta in multiplication term of A phi cap H phi complex conjugate, and this is equal to the A of R. So here A of R we are getting one because of the cross product of the A theta and the A phi we are observing one, and that's why we get it the A of R. So 1 by 2 real term of E theta and H phi complex conjugate we are getting one, where H theta complex conjugate is replaced by the E of theta complex conjugate upon the eta value. And finally the equation will be modified as a of R cap 1 upon 2 eta real term of E theta square. This is the particular equation we get it over there. So in all the total component we are getting one A of R eta I0 square upon 8 pi square R square in a bracket cos of KL by 2 cos of theta minus cos of KL by 2 bracket complete upon the whole term of sine of theta whole square. So this is the term we are getting one, and after observing this term we are trying to calculate the radiation intensity U, which is equal to the R square into average power density. So we just simply put the value of that, and finally this equation we get it. This entire eta into I0 square upon 8 pi square, this term is treated as a constant and it is represented as a beta B0, and this is the radiation intensity we get it over there. So normally for the particular different length of the dipole, here we are getting it the radiation intensity also, and this is the finally how to calculate the radiation intensity of that. Thank you very much.